I'll start real quickly. Waterloo Container, which many of you know is a family-owned business just like yours. We try to seek out world-class vendor partners. One of those for the past 10 years has been Amcor. Eric is a field service technician, has been with Amcor for quite a bit of time and does a fantastic job with their customers, with our customers and their customers. As a stocking distributor, we are their East Coast partner, and there are over 60 million caps literally residing in this building, ready to go out fast from freight. They can go out a box at a time. There's 1,350 in a box. The retail selling price for a Saranex liner, stock color, which there are 21 of. One of the ones that we just released is a new color, satin pink. We're calling it Rosé. It was actually on the Wine and Grape Foundation blast today. And most of the caps that are located in the building are Saranex liners that act, more similar to a traditional cork as far as O2 exchange. We do have the ability to allow you to customize your caps. It's a little bit of a process. It probably takes about 4 to 6 weeks to work through the art proofing. And then we can get it into a production queue, another 6 weeks. But what we would do is stock them here and send them out with your glass, with your deliveries as you needed them, and you'd pay as you take them. So that's the basic information. Eric is going to provide all the technical information. I think you'll find this very informative. And Eric is available to do field visits. And at some point, we'd love to have him in the Finger Lakes at a host winery and maybe do this in person. Thanks, Eric. Please take over as you see fit.
You bet. Thank you. Good morning, everyone, or afternoon, depending on where you are. So this presentation that I'm going to share is definitely not all encompassing. It's just really kind of look at it as more of a conversation starter and maybe to give people a little bit of insight of what it takes to apply a aluminum screw cap to a wine bottle properly, and then to hopefully calm some nerves of people who don't understand or that have been fed some misinformation, like your capping heads are set at the factory, don't touch them. This is not rocket science, and one of the things that I really like about applying aluminum screw cap to a glass bottle specifically, is that it's a very visual application. So let me get started on this presentation, and like Jennifer said earlier, use the Q&A option if you have any questions or want to interject anything. So the agenda, or the components of this presentation. Nomenclature. So the words that we use, the nomenclature that we use in screw capping is very specific, and so we'll go over that. The details of the cap, what we call all those different details, some of the bottle details, common application issues. This is probably going to be actually, let me take that back. We'll go over some liner choices, some special liners for special applications, common application defects and fixes. This is going to be the meat and potatoes of the presentation, and this is where I think hopefully you guys will take the most out of. And then some common quality checks that we that most of our users use, and hopefully if you're not doing these, this can give you some good data points to collect during a screw capping job, so that it really helps you, if you do have a problem, deal with quarantine size, and again, give you some relief that the cap is applied properly. Fancy. Screw cap terminology. So starting at the top and working our way down, if you look at the top right corner, there's a cap that has not been applied to the bottle yet, and you can see that the top is very square. But after application, there's a ring that's formed around the cap, and it's really rounding that corner at the top where the top meets the side. That is called a redraw. Some people also call it a reform. And what that's doing is when we apply this, because wines are sensitive to oxidation typically, We're applying the cap with a top and side seal. So the capping equipment is actually reshaping the top of the cap. And during that reshaping process, as you can see in the lower right corner, the liner is getting wrapped around the outside radius of the top of the bottle. And it's kind of getting pinched between that ring and the outside radius, creating a tighter seal. And really, this isn't about keeping liquid in the bottle. This is about controlling oxidation and controlling the way that gases flow through the liner and in and out of the bottle. I mentioned earlier that it's a very visual application. If you look here at where it says thread start, this is where the threading roller passed by the thread start on the bottle. That's where the threads begin at the very top, without having to change direction or without crashing into that thread start and causing a cut. Typically, if you get cuts at the thread start, it means your rollers are too high. So this is what we're looking for. We want to see the thread start on the bottle show up through the cap without the roller having to make a big jump or abrupt change in direction to get under the thread start. The tuck under is the groove that's formed in the skirt of the screw cap. That's the area below where the bridges break. And that's what locks the skirt under that ledge on the bottle that allows the cap to open properly and for the pilfer proofing or the bridges to break. Just below where the tuck under groove is formed, you have a support bead. That male bead that's formed into the skirt of the screw cap is very important to continue to have a nice aesthetic after the cap is applied. It's a stabilizing bead that keeps the skirt of the screw cap round. And then finally, everything below there is considered the skirt. That's really just an area to provide you for decorating a cap, to add some branding or to conceal the headspace. Typically on a wine bottle, the fill level is going to be somewhere just above the bottom of the skirt, but not always. And we can get into those reasonings later. Okay, now we'll get into a little bit of glass details. So in America, we have GPI. That's a committee of glass manufacturers all working together to make sure that they're working off the same specification. So the letter dimensions that I'm going to mention and the spec that I'm going to be referring to in this is the GPI spec for a 30 by 60 screw cap in a wine application. There are many, many different glass specs for different applications and different size of caps. So this is by far the most common spec, and the 30 by 60 screw cap is by far the most common screw cap used in a wine application. So this is going to be geared toward that combination. Just to give you a general idea of what the specification looks like, the GPI 1680, that -3 is actually the revision number, and that's the newest revision that's out there. You see that every dimension on the bottle has a letter designation assigned to it, and every one of those dimensions has a normal tolerance from the nominal dimension. And then there's also a second, on most of them, there's a second tolerance for maximum amount of ovality. So all of those things can affect the way the cap is applied. A lot of where successful screw capping comes from is how well the cap is supported by the bottle inside it and how pronounced those details are on the bottle to give the cap something to hold on to as you're forming the cap around those details on the bottle. So the S dimension, we mentioned the thread start earlier. So your capping head has the threading rollers set at a distance where the rollers are expecting to land directly under that thread start or S dimension on the bottle. But if you look at the GPI spec, the S dimension has a specification or a tolerance involved. So if your capping heads are set up a little on the tight side, let's say, or a little bit on the high side, this is where you might see an issue where one production, one run, you have no issues, and then you change bottle or batch of caps, and then all of a sudden you're seeing cutting at the thread start. And that's because these details can move slightly. Typically, those tolerances are 8 or 10 thousandths of an inch, so they're relatively small. But if you're on the ragged edge of cutting and then something changes, then obviously that's where these type of issues show up. So the next dimension is the D dimension. I'd say this is probably the one that glass manufacturers struggle with the most and cause our consumers or our customers the most problems. The D dimension is the distance from the top of the bottle down to where the tuck under happens. And so a lot of times this is what causes cutting in the tuck under groove. If that D dimension changes, again, your rollers are either too high or too low because the glass changed on you. The D angle, actually, I misspoke just a moment ago when I said the D angle is, when I said the D dimension is the one that causes the most problems, the D angle is the one that causes the most problems. And so if you go back to the glass spec, they have a zoomed in detail of this detail on the bottle. And so basically what you have is the D angle is the shelf that is formed for the cap to tuck under that ledge to hold the skirt onto the bottle when you open it. When this 15-degree max dimension goes beyond 15 degrees, or this radius, this outside radius gets too rounded off, you can see on the right side of the screen, there's an example of a picture from an optical comparator where that angle is well in excess of 20 degrees. It looks like 22, 21 degrees on the picture in the middle of the screen, middle lower. What happens is no matter how well you form the cap and form that groove to lock it under the ledge, the bottle has provided a ramp for the cap to reform itself right back up and over that ledge. Instead of it being a nice square edge that the cap can hold onto well, that angle gets ramped out, and then you have what we call a pull-off. A pull-off is when you go to open the cap and the skirt does not stay locked to the bottle. The entire cap and skirt come off as one instead of the bridges breaking as they're intended to do. The next one is the K dimension. Now, this is it's a rarer glass defect or an issue, but when it happens, a lot of times it catches people off guard and they don't properly identify this issue. So if you see on the right, you can see that there's a pretty substantial gap between the neck of the bottle and the bottom of the screw cap where they meet. That diameter of the neck of the bottle is the K diameter. And so what it is it's the diameter of the bottle. In metric, it's 59.5 millimeters down from the top. And that's basically the area in the zone where the skirt of the cap meets the neck of the bottle. When that diameter is too large, what happens is it creates a lot of resistance that is felt in the opening torque, or when you go to unscrew the cap, you feel that drag or friction being created by the skirt of the screw cap being tight on the neck of the bottle. Most people don't think about this, but when you start to open an aluminum screw cap, until the bridges break, the top and the bottom half turn together. So if that skirt is tight on the neck of the bottle, you feel that in the opening torque or the friction that's created by that neck being tight. So that's undesirable when it's too large. In the extremes of this, what happens is the bridges with the perforated part of the cap where the bridges are will actually invert, and the skirt will be tucked up underneath the cap, because when the cap is applied and all the downward pressure comes in from the top, the bottom of the skirt isn't able to scoot down the bottle. So then the next weakest area of the cap is where that perforation is. And so it basically just smashes the center part of the cap. Once you see it, you can't unsee it. And in this, when there's a K diameter issue, it almost always causes very high opening torques. The slip torque can be in the 20, 25 inch-pound range instead of normally, around 10. So it's pretty significant when this issue happens. On the other extreme, when the K diameter is too small, that can cause problems also, because the skirt, again, needs support to allow the cap not to flex too much while the cap is being formed around those details on the bottle. If there's no support for the cap flexes, and then you can break bridges during application. So liner choices. Over the years, Amcor has developed many different liner choices, and this isn't even all inclusive. And this is just talking about wine, not talking about all the different versions that are available for spirits, which is a whole nother category. Saranex and Sarin 10 are by far the most popular. I would say that Saranex is probably 80% of the liners that we use or that we sell in the wine market. The other close to 20% is Sarin 10, which is a tighter, less OTR liner choice. So you really have two choices, or two different ways of thinking as winemakers. If you have no concerns about reduction in your wine, or you know that the wine is going to be cellared for a long time, or if your winemaking style or maybe your varietal is super sensitive to oxidation, then Sarin 10 would be the most likely choice. Sarin X is a more breathable liner. It more closely mimics, I'd say, a general grade or a more normal middle of the road cork when in terms of OTR. And so if you have concerns about oxidation, or you know that this wine is going to go to market and be consumed relatively quickly, I'd say within a year or two, then Sarin X might be a better choice, because shelf life isn't as much of a concern, and the liner choice can help correct some concerns of reduction. We have special use liners. We have ones for use with pasteurization, and we also have liners for pressure. So in a semi-effervescent wine, I'm thinking like a Moscato that's been spritzed up with some CO2, something like that, where you've added CO2 to get some mouthfeel, but it's not quite to the level of carbonation where it would be champagne levels. We have the Stelvin P liner. That liner for pressure can hold up to 6 bars of pressure. So where the regular Sarin X or Sarin 10 in a semi-effervescent wine, the guarantee is up to 4 bar, and on a still wine, the guarantee is up to 1 bar. So it gives you a couple extra bars of pressure, confidence that you're not going to have leakage. And then again, we do have one for pasteurization that isn't necessarily meant for wines that are going to hold pressure the whole time, but can withstand heat and pressure for a short period of time while they're going through that thermalization process. Really, basic rules of choosing a liner are whether or not the liner has some sort of interaction with the liquid inside the bottle. So the neutrality, you can only know that. Now wine, we know how wine reacts with the liners, and there's no issue. But if it's something different, like let's say some sort of juice or something like that, we encourage customers to do testing on their own to confirm that there is no problem with liner either introducing or scalping flavors from the product. Reproducibility of the capping parameters. So in other words, the thickness, the density of the foam in the liner, all those sorts of things, and the consistency of those, so that they're similar to a liner that you may be choosing or switching from. We need to make sure that that liner is compatible with your previous choice. And then gas permeability, so really OTR. Let me go to the next slide and see what else we have here. Just to give you a general idea, this is using MoCon OTR testing equipment. And these are studies done by different companies, kind of showing some of the more popular choices that are out there and how those closure choices kind of measure up in terms of OTR. These ranges are in cc's per day per bottle. And you can see there 2 different testing facilities ranked Sarin X kind of right there in the middle of the spectrum of all those other normal, or not normal, but common closure choices that are out there. This is just to give you a general idea of what a Sarin X spec sheet looks like. If you ever see the term SX liner, that is comparable to Sarin X. We really shouldn't use Sarin X because Sarin X is a trademark name, and the liners that we are currently using are provided by another supplier that doesn't really own that trademark. So we're transitioning a lot of our literature away from Saranex and starting to use that term SX, just because, you know, we probably shouldn't be. But you'll see here that Saranex liners do have layers of PVDC plastic embedded in the liner composition. There is some pending legislation in Europe that's been being threatened for many years now to reduce the use of PVDC in food products. And so I don't think there's a slide on it in this presentation, but Amcor has developed a new line of liners called Stelvin Inside that are PVDC free. So if and when this legislation ever does go through, people aren't going to be stuck having no choices. So we've developed an entire catalog of liner choices that have similar OTR to Saranex and Sarantin, and then we also have a step that's in between. So if we have winemakers on the fence trying to decide, well, Sarantin is too tight of too low of an OTR for my winemaking parameters, Saranex is not enough, we do have a choice in between. Pasteurized and pressurized products. So I did mention earlier, oh, okay, we do have a slide on Stelvin Inside. Stelvin Inside, you have Sarantin, Saranex, and this says 4 different levels, but to be honest, the most breathable one we have discontinued because there was just no interest in it. We really didn't find any customers having any desire to use it, so we have just discontinued it and focused on the 3. One that's similar in OTR to Sarantin, one that's similar in OTR to Saranex, and then one kind of right in the middle. So the 702 is the one that's been discontinued. And again, the important thing about these are the elimination of PVDC. The reason that people are looking for the removal of PVDC in food product is it has to do a lot to do with the environment and recyclability. So when a screw cap is recycled, people aren't going to pluck the liner out. They basically just incinerate the aluminum, and the liner that's inside it is, you know, obviously incinerated at a much lower temperature than aluminum, and so it just burns off and goes away. The PVDC component, the C in that is chlorine or chlorides, and so it emits very tiny amount of chlorine gas, a toxic gas. So obviously people are looking to avoid that, and it makes sense. Okay, so now we're going to get into the common application defects and fixes. The picture here, the screen cap, is a good example of exactly what you want to see. Let me go back to that just real quick. There is a recap at the end of this where I'll kind of go over each detail of this, of everything that we see here on this capped bottle. But like I mentioned before, screw capping application is a very visual thing. We can see a lot of detail about the setup of the capper just by knowing what to look for and critically looking at the application of the cap to the bottle. But it's not only that. We need to know certain parameters about the screw capper also. So there are devices for measuring top load or vertical pressure. That's the pressure exerted by the capping head to the top, compressing the seal properly against the top of the bottle. And devices for measuring the pressure on the rollers that are forming the cap around the details on the bottle. So your 2 threading rollers and 2 pilfer or tuck under rollers. We measure those so that using the visual inspection, knowing what the application settings were, and including torque testing, we have much more confidence that the cap was applied properly. Pull-offs. Pull-offs is probably one of the most common problems that people struggle with when it comes to screw cap functioning properly. I mentioned earlier when we were looking at glass that the D angle of the bottle is a very pivotal part in this combination. If that D-angle gets beyond 15 degrees at any point on the bottle, that forms a ramp for the cap to unlock itself from and become a pull-off. Also, that outside radius where that ledge is formed on the bottle. The side pressure being used on the tuck under or pilfer rollers is another factor. How it basically controls how deep or how well you're forming that groove that is supposed to lock the skirt under the ledge on the bottle. And then from the manufacturing side, I see a typo. That's not how you spell strength. In the manufacturing part of the screw cap, the width of the bridges or how well that cap is perforated between the bridges is going to become a factor also. So this is one of the reasons why we do bridge break torque testing during our torque testing in the QC part, is if all of a sudden we run into a pull-off issue, it typically doesn't happen on every single bottle. So you'll still continue to get data coming in. So from that batch of caps. So you have data you can look at. And if all of a sudden your bridge break number is out of spec, well, then you already know what the problem is. The cap's defective. If your bridge break is normal, but you're having pull off, then you can, there are many troubleshooting steps that you can go to try to determine whether it's a capper issue or a glass issue. One of the things that I recommend to people a lot of times, especially if this just popped up in the middle of a run, is, if you're still on the same production date of caps, and even if you're on the same production date of glass, most wineries use their materials first in, first out. But when it comes to glass deliveries, they'll just do it by delivery, not necessarily by pallet number in sequential order. So if you've been running successfully for hours and then all of a sudden you run into pull off, I would look for specific cavity numbers to be repeating, because these glass defects of the D-angle going out of spec are time related. As glass molds get dirty, that D-angle starts to get more and more ramped out and that radius gets softer. So it kind of happens together as the molds get dirty. So if you're able to look at your pallet tag on the glass that's currently on the line, go back in your unused glass and see if you have a pallet from at least 8 hours earlier, then you can throw that glass on the line, see if the problem corrects itself. If it does, then you've already quarantined the problem and you know kind of what time frame. If you reach out to your glass manufacturer and give them that detail, they're probably going to be able to look at their production records and say, okay, well, anytime after this specific time, a changeover was done and that problem should be corrected. So it helps expedite things without having to go in and make adjustments to the capper. If you don't have that ability, let's say your glass was repacked and now it's mixed up. The first line of approach is to increase side pressure on the tuck under rollers or pilfer rollers, some people call them. And you can keep increasing pressure on the pilfer rollers or tuck under rollers in small increments, typically a quarter turn at a time, until the problem goes away. Hopefully in the first adjustment, it's going to be reduced or go away. If you increase pressure and you immediately start cutting in the tuck under, there is a phenomena where if your rollers are set up slightly too high, but the pressure is soft, the rollers may not penetrate full depth as they run into resistance of the cap being tight against the D-angle. And what happens there is as soon as you increase side pressure trying to overcome a pull-off, you'll get cuts in the tuck under. So the problem kind of shows itself as soon as you increase pressure. In that case, you would lower the tuck under or pilfer roller slightly. And the severity of the cut or the frequency of the cut will both help you determine how coarse of an adjustment that's going to be. Typically, when we're making adjustments to a screw capper, those adjustments are going to be small, like a quarter turn, very, very small adjustments to overcome these types of issues. Spinners. Spinner, again, this kind of goes back to nomenclature also. So I have found that sometimes people will call what I call a pull-off a spinner. So if you're calling me looking for troubleshooting help, I'm probably going to pick your brain a little bit and dig a little deeper instead of just trusting that we're using the same nomenclature. So on the pull off, some people call those lifters, and then they call a spinner a pull off. It gets confusing. So again, I'll dig a little deeper. But in my definition or my opinion, a spinner is when the threads are poorly formed, but the tuck under is good. So as you go to open the bottle, instead of the bridges breaking, the threads fail. And now you have a cap that just spins on the top of the bottle and will not open. The only way to open that bottle is to physically hold the skirt and hold the cap and twist in opposite directions to mechanically break the bridges, or get a knife out and cut the cap from the top of the bottle. Either way, that's a horrible experience for your customer. So we have tests to test for this during the quality torque testing phase that will give you some confidence that you're not going to be sending spinners out into the market. In addition to that, we go back to the visual. So if the thread is formed well visually and you're getting good strip torque performance when you're doing your torque testing, this is where you have confidence that the cap is not going to strip out when the customer goes to open it. Many different things can cause spinners. The most basic and first step of troubleshooting is always to verify your capping turret height. Make sure that the capper is set height, the height of the capper is set properly. If the capper is too high, something as small as just 1 or 2 millimeters of bottle height variation can cause random bottles to not be capped properly. So we really, first step, make sure the capper height is correct. If you've measured your side pressure on your rollers, on your threading rollers specifically, and it's low, it's soft, then the threads are not going to be formed and kind of well engaged on the threads on the bottle. That's going to create a cap that has an inherently weaker thread and is going to be more prone to spinners. Or if there's some sort of mechanical problem like the gold cap on the right, where there just really is no thread formed on the cap, any of those obviously are going to cause problems with how that cap opens. Bridge break strength can also factor into this. If we haven't cut that perforation correctly and the cap is resistant to coming apart, it becomes this tug of war over when you go to open the cap, whether or not the threads are going to fail first or the bridges are going to fail first. So we obviously monitor this during our production of your screw caps. We measure bridge width, and we also apply caps to bottles during production of each run of screw caps to verify that they function properly. And we do the same torque test that we recommend you do, so that when a customer reports back to us an issue, we have data that we can kind of compare. Broken bridges. These aren't as common as they used to be. About 6 years ago, we made some minor revisions to some of the details on our cap to help this problem. It used to be much, much, much more common. And this may sound kind of crazy, but what we did when we made this revision is where the perforation is and where the bridge line is, we moved that detail up just 1 millimeter closer to the top of the cap. And what that does is, by moving it that 1 millimeter, it moves it into a more stable spot on the cap and takes it further away from where the tuck under or pilfer rollers are doing their work. These two rollers, when they come in, there's a relatively significant gap between the bottle and the inside diameter of the cap. So as those rollers come in from opposite directions and start to form that groove, and then as they start to travel around the bottle, it ovalizes the cap and it creates this wave of flexing or moving material. And because the cap is weaker there, because it's been perforated, except for where the bridges are still connected, it can cause broken bridges. So I mentioned earlier, a lot of successful screw capping comes from how well the cap is being supported by the bottle inside it. So this is where that really becomes a factor. So if the details on the bottle are running on the small side of spec, but you're using a lot of pressure, let's say you're kind of at the extremes, you're causing the cap to flex so much that it could potentially break bridges during application instead of when the customer opens the bottle. So we don't want that. luckily for us is that a cap that has inherently weak bridges, let's say, also doesn't require as much pressure to keep it locked to the bottle and to separate when you open it. So the fix on this, no matter what the cause, whether it's glass or cap, is to just reduce pressure on the tuck under rollers in small increments to avoid that flexing. And this typically causes or cures the problem. There's another glass defect that isn't even written in this specification, and that is the amount of tilt or off level on the sealing surface on the top of the bottle. If the top of the bottle has a slight amount of tilt in it, the cap, sorry, my computer's trying to restart on me. The top of the cap tilts along with the tilt on the top of the bottle, but the skirt is trapped by its contact or its support by the neck of the bottle. So you create this situation where the cap actually has to be kinked. And so in that case, you're going to see broken bridges on the same side. And on the opposite side, you'll typically see the bridges even kind of crushed closed. And so that's a different scenario, much, much more rare. Either way, reducing side pressure slightly on the tuck under or pilfer rollers can usually clear this up. That being said, the only caveat is if you reduce pressure too much, you're more likely to go back into a situation of having pull-offs. So the industry kind of standard or the norm here is that people will allow 1 or 2 broken bridges, but no more than 2, especially if it's not every bottle. They typically aren't going to worry too much about this because from a legality standpoint, you still have pilfer proofing. It's still obvious that this cap has not been opened. You still have the other 6 bridges intact, proving that that cap has not been opened. Cutting in the tuck under, this is another relatively common one. And this kind of goes back to, actually, I don't know if I mentioned this, but as the capping head, just kind of how the capping process works. As the capping head comes down over the capped bottle, the pressure block is the part that actually makes contact with the top of the bottle. That part compresses the seal, forms the redraw or that ring in the top of the cap, creating the top and side seal. While the liner is held in compression, then the 4 rollers, the 2 threading rollers and the 2 pilfer rollers, will start to form the cap around the details or the thread and the tuck under on the bottle. While the capping head has the rollers engaged on the cap, it makes 2 full revolutions around the bottle. So you can see this in inspection of a capped bottle. You can count the number of revolutions that the thread rollers were engaged on the cap. But the reason I mentioned it now is because you see how the cap on the right, the kind of goldish color cap, has a cut all the way around. Theoretically, even if one of your pilfer or tuck under rollers was too high, because it makes 2 full revolutions around the cap, you should see a cut that goes all the way around the circumference of the cap. Realistically, in order to do that, your roller has to be very, very high, way too high, to the point where somebody has probably got in there who didn't know what they were doing and made a very coarse adjustment to cause this. The D angle on the D dimension on the bottle can cause this. If you were set up relatively tight on a bottle with a minimum D dimension, and then you get into a batch of caps that has a max dimension, it could cause this. Liner thickness can cause this. If you have, let's say you switch from a batch of caps from a different supplier and they use a liner that has a different thickness or a different density, and the cap is now relatively sitting a little higher on the bottle, that effectively raises the height of all 4 rollers, and that can cause a cut like this. But more realistically, when we see cutting in the tuck under, it's more typically like what we see on the blue cap, and that is a tiny cut, maybe a 1/4 inch long or less. When you open that bottle, it may even open up more and cause a bigger cut. So again, the frequency of the cut and the intensity of the cut are going to help you dictate how big an adjustment you're going to make to cure that problem. You can do that in a reduction of side pressure in small increments, but knowing that if you go too far, you can create a pull-off, or you can go down with the rollers to create room for the aluminum to tuck under the D angle on the bottle but above the roller that's forming that groove without being pinched between two hard surfaces. So the visual inspection. So I think I have some animation on here. Nope. Let me go back. The visual inspection, starting at the top and working our way down. Again, you have the redraw. That's that ring that's formed at the top, creating the top and side seal. You're probably used to seeing what that looks like on your capping equipment. Different manufacturers can make that look slightly different. So if you're looking at bottles on a supermarket shelf, let's say, or in the wine shop, and you see some that look more defined or less defined than others, it can just be by manufacturer. It can be by the amount of top load used. And if people are in the habit of fudging their machine height up and down to cure capping problems, the manufacturer gives you one way of setting your machine height, and that is where the machine should be set. There is no troubleshooting step where you raise or lower the capper. When you raise the capper or lower the capper, what it does, let's say you're cutting the threads and you raise the capper, just 1 or 2 millimeters, maybe 3 millimeters. What you've really done is you've reduced top load. So now you're not compressing the seal properly anymore. You've potentially reduced side pressure on all 4 rollers because now the rollers aren't being drawn in full strength. So the spring adjustment that you typically adjust to adjust pressure on the rollers, now you've adjusted all four rollers to correct just one problem. And you've also changed the timing of when the rollers engage the cap and when they disengage from the cap. So you've changed everything about the capping concept to correct one problem. And it can work. Don't get me wrong, it can work. It's just not the right thing to do. So I highly discourage people from doing that. If you have people on your lines in the habit of doing that, again, training is available, and I would love to come out and help people get up to speed and show them why it's not the right thing to do. Moving down from the redraw, you have the threads. And if you look at this cap, I don't know if you can see my cursor or not, but the thread start shows up very clearly through this cap, but you can see that as the threading roller passed by the thread start, it did not have to change direction severely to go by it, and there is no cut at the thread start. And then from where the threading roller engaged to where the threading rollers ran out of thread on the bottle and popped back into the thread above it is 2 turns of rotation. That's what we want to see. That tells us that the capper height is correct and that the threading rollers are adjusted correctly so that they're catching all the thread that's available on the top of the bottle, creating the most robust thread that they will, and creating a cap that's always going to open properly and keep a good seal. Moving down from the threads, we have the bridge line again. And I didn't mention earlier, but this cap just reminds me, sometimes there are horizontal lines along here that's called knurling. That is optional. It has no functional use. It's purely cosmetic. So caps can be produced with or without knurling. But on the bridge line here, we can see that there are no broken bridges. Moving down to the tuck under, one thing I didn't mention when we're setting up the capper, one thing we look for is if you look at the profile of this groove formed by the tuck under or pilfer rollers, you can see that it's kind of like a greater than or lesser than symbol. It has a bevel on the top and a bevel on the bottom from the deepest part of the groove. If you look at that groove and it's formed like this, where it's very, very straight in across the top and way more beveled on the bottom, that's also a visual indicator that tells you that your tuck under rollers are adjusted relatively high. The opposite is true. If they're low, then that bevel is going to be like this. It's going to be more beveled on the top and more straight in on the bottom. Again, they're just visual indicators. And then just below the tuck under is the support bead you see here. If your tuck under rollers are too low, there's this phenomenon or defect that is caused. It's a visual defect. It has no effect on capping. But what happens is that material that is raised from the skirt and kind of poking out, that material will actually get drawn into the groove and it will be erased from the cap. That's when the skirt starts to get all lumpy and jagged and flat spots in it, that's a sign that your top counter rollers are too low. So again, visually, there's a lot to see there as long as you know what you're looking for. And I hope that helped. So next are the common torque tests that we recommend people do. And then I think we're about done. So time-wise, I don't know how we're doing. If George or Jennifer, if you want to interject, kind of let me know. Anyway, we'll get into QC checks. So there are 3 torque tests that we recommend our customers do. And again, this is about not only quality control, but collecting data points that help not only in troubleshooting, but also in quarantine if and when you do have a problem. These tests will really help you identify when that problem started and kind of how far you have to go back to quarantine once a problem is discovered and corrected on the bottling line. So there are 3 torque tests: slip torque, bridge brake, and reverse. Some people also call that strip torque. So basically the way they work in order: slip torque is when you grab the cap and you start to twist it in the opening direction. It's the amount of effort or force while the bottle is clamped into a torque meter as the cap begins to move. It's really what you're measuring is the friction of the liner slipping across the sealing surface of the top of the bottle. There are many other things that create friction that are felt in this test, but really what you're wanting to feel there is the friction created by the liner against the sealing surface on the top of the bottle. This test should be relatively consistent within 1 or 2 inch-pounds of each other, bottle by bottle, throughout an entire capping run. Bridge brake is the amount of force that it takes for the bridges to break on the cap. So we take the same bottle that we've done this on. After zeroing the meter, we continue in the opening direction until all 8 bridges break, and then record that number. The reason we separate these out is really twofold. By measuring bridge break, it's the one torque test that you do, that we recommend you do, that you as the user of the cap have the least control over, because this is more about the manufacturing of the bridge line and how well we have cut that perforation in the cap. But where it really becomes handy is 2. 1, when we do the next step, the reverse or strip torque, it gives you a target to know whether what you need to be a pass. But also, if you're struggling with pull-off or spinners or something like that, it gives you the data point you need to know how resistant the cap is from separation. So if you're having really high bridge breaks and you're also having pull-off, it very well could be a cap problem. But back to giving you the target for the reverse or strip torque. So the 3rd test is taking that same bottle that you've just done the slip and the brake on, back in the tightening direction now, zero your meter again, and measure in the tightening direction to see how much force it takes to completely cause the cap to strip out, the threads to fail. In order for this test to be considered a pass, the amount of effort that it causes the threads to strip has to be at least 4 inch-pounds more than your bridge brake. This is your test that gives you that confidence that the cap is not going to become a spinner. I mentioned earlier, that's the worst defect you can send out into the marketplace, because consumers get really upset when they have to cut the screw cap from the top of the bottle with a knife. So by doing this strip torque test, what you're doing is you're verifying that your threads are significantly stronger than the bridges, and that by doing that test and making sure that they are significantly stronger, that there is theoretically no reason why this cap should ever become a spinner, because that tug of war is always going to be won by the threaded portion of the cap, and the bridges are weaker, so they should break before the threads fail. And I really hope everybody enjoyed this. That's it for the presentation. So I think we're going to do a little bit of Q&A. I see that there's something in the chat here. Let me see. Should the cap be able to move 2 or 3 millimeters before the bridge breaks, or should the cap not move at all? Great question. Yes, the cap should move before the bridges break. If you have your tuck under rollers adjusted so tightly up underneath the ledge on the bottle that when you go to twist the bottle or twist the cap, the bridges want to break immediately, chances are you're going to also have random cutting in the tuck under. It doesn't have any effect on seal or anything like that, but there's always some random difference from bottle to bottle. No matter how great your glass supplier or manufacturer is at producing glass is inherently a moving target. And so because of that, we typically adjust the tuck under rollers a little bit lower so that when you see a little bit of tilt in the top of the bottle or any sort of deviation, you're not going to automatically have a capping issue. We try to set up the capper with some forgiveness built into it so that it can deal with these minor variations from bottle to bottle. Typically, if you're set up that high, you're going to cut. The other thing that can cause by having your tuck under rollers adjusted that high where you have very little rotation or no rotation before bridges break is random pull-off issues. When your roller pressures are soft, but I'm going to try to talk with my hands here. So let's say this is the D angle on the bottle. The tuck under or pilfer roller should come in somewhere like this. But if they're too high and they're coming in against that D angle, the aluminum of the cap has to pass in between the ledge on the bottle and the tip of the roller without cutting. So if the pressure is soft, it may not cut, but it will also not penetrate full depth. So you're more likely to get a pull-off in that situation also. Then if you realize you have pull-offs and you try to increase pressure to overcome that, that's when you'll cut automatic or right away. So in that case, you would lower the tuck under roller slightly and it would probably problems. So I hope that helps.